The force that accelerates the pod was first detected by French physicist André Ampère in 1820. He noticed that when the currents in two parallel conductors were flowing in the same direction, the conductors attracted each other. But when the currents were in opposite directions, the conductors repelled each other. Ampère reasoned that the magnetic fields around the wires created attraction and repulsion forces. The left-hand rule for a conductor predicts the direction of the field around each of the wires. When the fields in between are in the same direction for each of the wires, repulsion occurs. This repulsion is similar to what happens when two bar magnets are placed side by side, so that the field of one magnet is in the same direction as the field of the other magnet. When the electron flow in two wires is in the same direction, then, in the space between the wires, the field produced by one wire runs in the opposite direction to the field produced by the other wire. As a result, the wires are attracted to each other. Again, this is similar to two bar magnets placed such that the fields between them run in opposite directions. The direction of the force on a current-carrying conductor placed in a magnetic field can be easily determined. If the electron flow is in this direction, the field produced around the conductor will interact with the field produced by the magnets. Since the two fields are in the same direction above the conductor is repelled downward. If the direction of electron flow is reversed, then the field around the conductor also reverses. The fields are now in the same direction below the conductor, and so the conductor is repelled upward. This effect is called the motor principle. The motor principle is one of the most important applications of Hans Christian Ørsted's discovery of electromagnetism. But it was British physicist Michael Faraday who in 1821 put all the pieces together and devised the first electromagnetic motor. The motor principle states that if a current-carrying conductor is placed within an external magnetic field, it will experience a force which is perpendicular to both the direction of the electron flow and the external magnetic field. The direction of the force is determined by the line of electric motors. A loop of wire carrying a current is placed between magnetic poles. If we apply the left-hand rule for force on this side of the loop, so that the thumb indicates the direction of electron flow, and the fingers indicate the direction of the external magnetic field, then the force on the conductor will be upward as indicated by the palm. When the left-hand rule for force is applied to the other side, the palm indicates a downward force. These two forces will cause the loop to rotate about an axis until the loop is vertical. If it rotates past the vertical, these same forces will stop the rotation and return the loop to the vertical position. But to perform work, the loop must continue to rotate. This is easily accomplished by directing the electron flow through a split ring called a commutator, which is in contact with graphite brushes. Initially, electron flow is in the same direction as shown earlier. Then the loop rotates as before. But as soon as the loop passes through the vertical plane, the commutator causes the electron flow to reverse. This reverses the direction of the forces on the sides of the loop, which causes the loop to continue rotating. The split ring commutator reverses the electron flow in the loop every half rotation, just at the instant it is required to keep the loop rotating. Normally, we use electric energy to run a motor. But could we use a motor to produce electric energy?
Volta's work eventually led to the development of batteries, which could be used as sources of continuous charge flow. A battery like this was used by Danish physicist Hans Christian Ørsted in 1819 to conduct an experiment in which he hoped to prove conclusively that electricity and magnetism were not related. At first, the demonstration seemed to work. When the switch was closed, the compass needle, which was perpendicular to the conductor, didn't move at all. However, when Professor Ørsted repeated the experiment, this time with the needle parallel to the conductor, and the switch was closed, the compass needle reacted instantly. So it seemed obvious that electricity and magnetism were somehow related. As a result of Ørsted's experiments, French physicist André Ampère made a detailed study of the magnetic field about a conductor carrying a charge flow. Using iron filings, he demonstrated that there was a magnetic field around the conductor. The pattern formed by the iron filings created a series of concentric circles. Around the conductor will be in one of two directions. With the electron flowing this way, the magnetic field around the conductor is in this direction. Reversing the flow of electrons doesn't affect the shape of the pattern, but it does affect the direction of the field. Reverse the electron flow through the conductor, and the magnetic field direction will reverse as well.